In the first example on the board from this chapter, what I'm going to do is I'm going to begin with the definition we have of magnitude, where we say the difference in flux between two stars is related to the magnitude difference between two stars in this manner. And I'm going to demonstrate that this equation is fundamentally equivalent to this equation down here. Now, where does this equation come from? Remember that we defined magnitude as saying magnitude of 5 orders of difference will mean one object is 100 times brighter than the other object. So that basically means if object A has magnitude equal to 1, object B has magnitude equal to 6, that means the flux of A is 100 times the flux of object B. Now, I don't have to necessarily have the numbers 1 and 6 right here. I could have numbers like 0 and 5. 0 magnitude is still 5 orders of magnitude brighter than object B. Or I could have something like 11 and 16. Again, we're 5 orders of magnitude greater. That means we're going to be 100 times dimmer in this case. So what we did, we extrapolated this idea and we said, okay, that means FA over FB is going to be equal to 2.51. There are a few other decimals after this 2.51, but we're just ignoring them. We're rounding. And then I raise that to the power of MB minus MA. I'm going to begin with this equation. I'm just going to do some algebra, some arithmetic to it, and we're going to end up at the other equation. Now, again, like I want to emphasize, the reason that I am doing this calculation is it is important to me that you believe what I say, not because I say so, but because it is natural to you. In the homework on the exams, you will not need to do any type of calculation like what I'm doing on the board here. So we learn in grade school and high school that if you do something to one side of an equation, you have to do it to the other side as well. So what I'm going to do is I'm going to take the log of both sides of these equations. So I could write log of FA over FB is equal to log of 2.51 raised to the MB minus MA. I do something to one side, I have to do it to the other. Now, there is a property of logarithms that in general, if I write log of x to the y, this is equal to y times log of x. This is just a property of logarithms. You could look it up on Google, Wikipedia, see other properties of logarithms as well. Now, if I look at this, I could say, well, I could associate downstairs here is x, downstairs here is 2.51. I could associate upstairs here, I wrote as y. Upstairs, I wrote as this entire thing, MB minus MA. So if whatever is written upstairs comes in front, here, whatever is upstairs in the exponent will come in front. So I could then write the log of FA over FB is equal to, we'll bring whatever is upstairs in front, MB minus MA, and because that was everything upstairs, I'm going to put it in parentheses just to keep it nice and neat. Then I will have log of 2.51, log of whatever is downstairs. Okay, what I'm going to do next is I have log of 2.51. that is something I could just go ahead and put into a calculator. So if I write log 2.51 in a calculator, I hit equals, this entire term is equal to 0.4. So now I could write this as log of FA over FB is equal to, I'm going to put the 0.4 in front here. It just looks a little neater in my opinion. So 0.4 times MB minus MA. What I'm going to do next is I am going to divide 0.4 from the right side and from the left side, because again, whenever I do sign to one side, I have to do it to the other side. So I could take both sides of this equation and I could divide by 0.4. So divide by 0.4. Divide this by 0.4. And when I do that, I have 1 over 0.4 log of FA over FB is equal to, well, again, from the last video, we said when you have the same thing in the numerator and denominator, the same thing upstairs and downstairs, they cancel. So these guys will cancel with each other. So all I'm left with is MB minus MA. And the very last step I'm going to do, 1 over 0.4, that's the same thing as all that over 0.4. I just kind of brought the 0.4 out front to make it a little bit neater. 1 over 0.4 is equal to 2.5. So this term over here is equal to 2.5. So then I am left with 2.5 log FA over FB is equal to MB minus MA. So what I have done in this derivation is we have begun with the equation FA over FB is equal to 2.51 MB minus MA. And what we did is we have shown that these two equations are fundamentally the same thing. They both give us the exact same information. The reason we have two equations is depending on the problem we're trying to solve, sometimes this equation will be more convenient to work with, sometimes this equation will be more convenient to work with. As a first example problem of something that will resemble what you might see in the homework, you are given that the star Rigel is 1.32 times as bright as the star Betelgeuse, and you are given that the magnitude of the star Rigel is 0.12. So given this information, what is the magnitude of Betelgeuse? The first thing I'm going to say is we have two possible equations that we will consider useful to solving this problem. We could use this first equation or the second equation. So how do we know which one we want to work with? The rule of thumb I'm going to say is if you are trying to find a magnitude, use this first equation. If you are trying to find a flux or a brightness or how many times brighter is star A compared to star B or something of that nature, use the second equation. Why am I saying that? Well, it is easy to solve for an unknown when the unknown is out front. So if I'm trying to solve for FA, I just have to multiply FB to both sides and then I can find FA. If I'm trying to find a magnitude, I could plug in the known magnitude, look for the unknown magnitude, that's fine. But if I were to try to find the magnitude of Betelgeuse using the second equation, well, the magnitude of Betelgeuse is upstairs here in an exponent. And I would need to plug numbers in. I would need to somehow isolate this exponent, get this exponent downstairs, and that's going to be a mess. Not that it can't be done, but we would have to use math similar to what we did just earlier in the derivation I did before this video. Similarly, if we were asked to find a flux, or how many times brighter is star A compared to star B, well, the flux is buried here inside a logarithm, so I would need to somehow get rid of this logarithm and get these fluxes outside the log, and it just ends up being more work. So I'm going to want to use this equation right here. Secondly, we are told that the magnitude of Rigel is 0.12. The magnitude of Betelgeuse is the unknown we're trying to find. This equation, as it's written right now on the board, has A and B, but there is nothing fundamental or special about A and B. A just means star A, B just means star B. So to help my mind keep track of things in a problem like this, because sometimes you might have other stars like Alnitak and Mintaka, or whatever, Polaris and, I don't know, some other star, Vega. Remembering which is star A and which is star B, I'd rather have something I could quickly look at and see. So I'm going to say star A will be Rigel, and star B will be Betelgeuse. And then instead of writing A and B over here, I'm going to write this as MB minus MR is equal to 2.5 log FR over FB. Just coincidentally, B happened to be Betelgeuse in this problem. And here now, I know very quickly when I'm looking at anything with the subscript R, I'm talking about Rigel. If I'm looking at anything with the subscript B, I'm talking about Betelgeuse. So I'm just using semantics here, but I'm making my life a little bit easier where I don't need to quite think as much. The final thing I'm going to say before we plug numbers in and solve this is, in this problem, we have two symbols. We have FR and FB. But over here, we only have one number. So how do I think about this? Don't I need a second number so I could plug something in up here and something else in down here? Not really. Let me make an analogy. So let's say I have $100, hooray for me, and you have $125. Even better for you. Hooray for both of us. In this case, we could say you have 25% more than me, which is also equivalent to saying you have 1.25 times what I have. I have 100, you have 125, you have 25% more. Or another way to phrase that idea is you have 1.25 times what I have. The amount you have is bigger than the amount I have. That's why the number of times you have what I have is greater than 1. But there's nothing really special or fundamental about 100 and 125. If I were to say instead, I have 400 and you have 500, this is better for both of us. I fully support this. The statement, you have 1.25 times what I have, still holds true. And if I say I have $10,000 and you have $12,500, again, you still have 1.25 times what I have. So in every case, I could say 125 over 100 is equal to 1.25, but I could also say 500 over 400 is equal to 1.25, or I could say 1250 or 12,500 over 10,000 is also equal to 1.25. In all of these scenarios, the amount you have is 1.25 times the amount I have. Similarly, if I were to say instead of money, I'm going to say, let's say Betelgeuse gives off 100 units of light. That means Rigel gives off 132 units of light. Or if Betelgeuse gives off 10,000 units of light, Rigel gives off 13,200 units of light. It's not the individual numbers that are important, it's the ratio that's important. So I don't know how bright Betelgeuse is, I do not know how bright Rigel is, but I know how many times more Rigel is brighter than Betelgeuse. It's like saying, if I say you have 1.25 times more money than me, you don't know which of these is actually true, but you do know that no matter what, you do have 1.25 times more than I do. So this statement is saying that the brightness of Rigel over the brightness of Betelgeuse is 1.32. So FR over FB is equal to 1.32. So even though I have two terms in the parenthesis up here, I'm just going to be plugging in a single number inside that parentheses. We are already given that ratio. So I could write this as MB minus MR equals 2.5 log of 1.32. Okay, we are also given the magnitude of Rigel, so I'm going to just plug that in as well. So I have magnitude of Betelgeuse minus magnitude of Rigel, which I said was 0.12, is equal to 2.5 log of 1.32. At this point, we have all the numbers plugged in. We have the magnitude of Betelgeuse out front. We just need to do the arithmetic and solve for the magnitude of Betelgeuse. So the first thing I would do is I would go to a calculator. What is the log of 1.32? That's just something you plug in a calculator and hit enter. When you do that, you get this term as 0.12. So I could then write MB minus 0.12 is equal to 2.5 log, 2.5 times 0.12. I would have a line that looks like that. Next, you have your orders of operations to remember. You multiply and divide before add and subtract. So I'm going to multiply 2.5 times 0.12. If I do that, I get 0.3. So this term here is equal to 0.3. So I have M Betelgeuse minus 0.12 is equal to 0.3. Again, I want to isolate M Betelgeuse all by itself. I have to get rid of this 0.12. So if I want to do something to one side, I have to do it to the other. So I could add 0.12 to both sides. So if I say plus 0.12 plus 0.12 on both sides, I would have M Betelgeuse minus 0.12 plus 0.12. That cancels each other out. And then here I would have 0.3 plus 0.12. Here I saw a negative sign, and in order to kill the negative 0.12, I know I have to add it because I want to get M Betelgeuse all by itself. And then after that, 0.3 plus 0.12, I find the magnitude of Betelgeuse is equal to 0.42. In the next example problem, we are given that when Jupiter is at its brightest as seen from Earth, it has a magnitude of negative 2.94, And when Jupiter is at its dimmest, as seen from Earth, it has a magnitude of negative 1.66. For context, the brightest star in the nighttime sky, Sirius, is dimmer than Jupiter when it is at its dimmest. So Jupiter is a really bright object. So this is Jupiter when it's at its brightest. And this is Jupiter when it's at its dimmest. So just remember, magnitude, more smaller numbers or more negative numbers mean brighter. So it's kind of an inverted scale. Even though in many problems we compare two separate objects, like in the previous problem we compared the stars Rigel and Betelgeuse, there's no reason we have to do that. I could compare an object at one time versus another time. If you play sports, you could compare your speed at the peak of your season versus at the beginning of your season. And those are still valid concepts, still valid bases for comparison. So we have two equations here. How do we know which equation we want to use? Well, we said before, the rule of thumb is if we're looking for a magnitude, we want to use this equation. If we're looking to compare brightnesses or compare fluxes, which for this course effectively mean the same thing, we will use this equation. The reason for that is if I have my knowns, if I plug my knowns upstairs in the exponent, that's just then a number I need to solve. If I plug my knowns inside a logarithm, that's just a number I need to solve. If I'm trying to solve for an unknown that's in an exponent or in a logarithm, I need to somehow free it from the exponent or logarithm. And then I need to do math similar to what we did in the derivation before the previous example problem. Not that can't be done, but it's just extra steps that are not necessary. So because we are given magnitudes, we are given these values, and we're asked to compare brightnesses, I will use this second equation. Now, another thing I'm going to say that we did in the previous problem was there is nothing fundamental about the letters A and B over here. They are just placeholders to designate something. So I am going to designate Jupiter at its brightest is A, and Jupiter at its dimmest is B. And I'm going to furthermore write it as FDim and FBr for bright. So when I rewrite this equation with these new subscripts, I would have FBr over FDim equals 2.51 MDim minus M bright. Okay, so you might be wondering, why not just brightest starts with B? Why not just have bright BB and dim BA? The reason I wanted to do that is I'm going to make my life a little bit simpler down the road. I know at its brightest, Jupiter gives off more light than when it's at its dimmest. If Jupiter gives off more light when it's at its brightest, that means FBr will be larger than FDim. And when I divide a big number by a small number, I get something greater than 1. The problem is asking for how much brighter is Jupiter when it's at its brightest. So I want Jupiter at its brightest to be upstairs, which is why I chose F bright to be A and FDim to be B. And just to help alleviate, make the problem a little bit neater, I included a few extra letters in my subscript. So again, just like the example previously with money, we don't know how bright Jupiter is at its dimmest and how bright Jupiter is at its brightest, but we want to know how many times brighter it is. So we're comparing two numbers, even though we don't know what the value of those numbers actually is. So I have a number for the magnitude at its dimmest. This is MD. So this is MDim. This is M bright. So I could plug these numbers in. Now, when we plug numbers in and actually go through the math and solve, it's going to be very important beware of signs, positive and negative signs. If you subtract a negative number, that's like adding a number. That will come up a fair amount in problems like this, so be aware, just go slow, be careful. So I could say F bright over F dim is equal to 2.51. The magnitude when it is dim is negative 1.66. I'm going to write this bigger just so I don't accidentally confuse and think this is downstairs. 2.51. Then I have negative 1.66 minus negative 2.94. I included extra parentheses just to be careful. Now, when I look at this, before I take any exponent, I first need to solve this. Because your orders of operations, you do exponents before multiplying, dividing, which that you do before adding. So negative, negative becomes positive. So this side is essentially written as 2.51 raised to the power of negative 1.66 plus 2.94. 2.94, negative 1.66. When I add those two numbers together, I get 1.28. So I get 2.51 raised to the 1.28. And at this point, I don't know how to solve this by hand. I just go to a calculator, I write 2.51, I raise it to the 1.28, and when I hit enter on my calculator, I get 3.25. So what that means is F bright over F dim equals 3.25. So again, I don't know how bright Jupiter is when it's at its most dim, and I don't know how bright Jupiter is when it is at its absolute brightest, but if Jupiter has a brightness of 100 when it's dim, Jupiter will have a brightness of 325 when it's at its brightest. Or equivalently, if Jupiter has a brightness of 1 million at its dimmest, Jupiter will have a brightness of 3,250,000 when it's at its brightest. I'm comparing these two numbers. I don't know the actual value for individual numbers. So, as I said, when I have something, I could say F bright is 3.25 times the value of F dim.